Yeah, okay. Thank you a lot for giving me this opportunity to come to IBS to give talk. So very shortly, this is an ongoing project with my collaborator Graham, who is a postdoc in Triumph. And the idea of this project was to try to constrain or study the neutrino mass models using the gravitational wave signals from the phase transitions. Okay, that's the main thing in short. I will go like a very small introduction with a little bit of background of neutrinos with review. Then I will talk about the model particular I'm choosing for studying in this project. Then the gravitational wave physics, and then in our model we have a confinement, so I will talk a little bit about that and then the conclusion in principle. Okay, stopped working. It doesn't work anymore. Now it works again. Thank you. So, as an introduction, technically, the idea is the following. The standard model doesn't have the neutrino mass, so you need to go BSM to get the neutrino mass. Okay, so the possibility is that this can be 3 level, this can be. So technically, we're trying to understand when you complete the neutrino mass, in what cases you can connect this to gravitational waves. Of course, the assumption is that we have to assume that if we see some kind of gravitational wave signal in the future, that this is something to do with the neutrino mass origin, okay? Just like other people do assumption about, for example, when the seesaw scale is connected to gravitational wave signal, okay? Similar story. So in our case, we discussed this more, okay, we discussed these things. Neutrino mass, non-abelian dark sector in our model, then connection with gravitational waves. And we tried also to study the neutrino genesis part, since it usually exists in most neutrino mass models, so that's like optional. And we're trying to connect all of the above. Of course, this is not possible in many models, but okay, we try to look at the one that we can correlate these things. So when people create a neutrino mass model, usually you ask the questions like, is it Majorana or drag type? Is it a 3-level or radiative? What kind of new particles you add? And maybe you extend the gauge sector. Of course, all of this change the things you get and the difficulties you have to face. Because in some cases you get dark matter, in some cases you can explain more things, in some cases you have cosmological problems. And so looking at this, the most common, well-known neutrino mass models from 80s and 90s are the 3 at the 3 level. So one of them is the seesaw 1. So all of them generate the so-called the Weinberg operator from 1979, which looks like this, which is the only operator of dimension 5 in the standard model extension. And for the seesaw 1, you add the fermion singlet. You get this kind of diagram for the neutrinos. This is your Lagrangian. You get this kind of mass matrix. And the idea of the seesaw is that there is something heavy which makes the neutrino masses naturally small. The other way to look at this is that the Yukawas can be very small and the mass can be reachable in the colliders. So there is 2 options for this. The next one is the so-called seesaw 2. You add the scalar triplet in this case. The Lagrangian looks like this. This is the diagram. So you kind of like what you're doing is your Higgs wave induces the triplet wave, which is small because of this parameter here. And the naturalness of this being small is that if you remove this term, the lepton number is conserved, obviously. Okay, so by introducing it, you're breaking the symmetry. The third one is the seesaw 3. The diagram is the same as seesaw 1. The mass is the same. Technically, from neutrino point of view, it's the same thing, just the phenomenological difference is that it's a singlet versus triplet. Okay, so this is the third variation. Then people did some attempts on different variations of the seesaws. So there is like, as I know, there is 2 different approaches for this. People can like write down this kind of mass matrix and then try to play with it. And for example, This thing is known as the inverse seesaw, because here, in order to generate a small neutrino masses, you don't need something heavy. You need something small, which is M2. So if in the normal seesaw, small neutrino mass is explained by something large, in this case, the small neutrino mass is explained by the small ratio of mg over mn times the small m2. And the logic is that m2 is small because it violates Lipton number, and if md is the electroweak scale, mn is some kind of physics at the higher scale. So you kind of get this natural explanation. The other variation, for example, there is a linear seesaw, so-called, which is very similar to the inverse, but you have the zeros on the diagonal, and the only term that violates Lipton number is md prime, and the neutrino mass is small because of the combination of the ratio and the md again. Okay, there is other variations exist, but I decided to put 3. Next, if you go to the loop level, then again we have 3 one-loop realizations at one loop level. So the very first one was done by Z in '86, where you have the 2 Higgses attached to the opposite sides, one at the Fermi and one at the scalar side. If I'm not wrong, he did this with the standard model leptons here, but this model today is excluded. I think some variations of it might exist. The next one is the 2006 scotogenic model that was done by Ma. For that, you have to add Z2 symmetry in the loop. You add a singlet Majorana-like particle N fermion, and the doublet Z2 or doublet. So it falls in the context of 2 Higgs doublet models. In this case, inert, because the gas inside the loop has a Z2 odd. Okay, so this was done in 2006. Then the third variation is when you attach the 2 Higgses at the fermion line. In this case, this gives the so-called radiative inverse seesaw variation. We have done this in 2014. In this case, you need the lepton-like doublet, so quantum numbers are the same. S singlet, in our case it was real, and N Majorana, all Z2 are odd under the new imposed symmetry of Z2. There is a possibility you can generate all these models using GATS, where these symmetries are not like put in by hand, but like derived from the gauge groups. That's people have done that too in principle. So there is technically different approaches to this. Next, so if we would do a drag neutrino, then you have to be more careful, and there is more things to do, because in order to get the drag neutrino, you first have to forbid the Majorana mass term of the N. So you have to put the right-handed neutrino. You have to make it not singlet under something. In this case, we call that symmetry S. This can be discrete, global, gauged, dark symmetry, many variations possible. Okay, but the key is that there must be something else, or some people just say we assume it's forbidden. So if you ask the question like how many ways are there to do, so there is 4 ways exist at the tree level. So first one is analogous to CC1 in some sense. When you contract the Higgs doublet with the neutrino together and you get the singlet, so you have to add this N vector-like singlets. And these crosses indicate where the S symmetry is violated. The assumption is that the right-handed neutrino is not singlet under S symmetry, and the left-handed or the standard model guys are singlets, okay? The L and the Higgs. So in this case, S has to be violated either here or here, depending on what kind of S is, okay? If it's gauged, then you need extra Higgs and so on. The second variation is the CSO3 analog guy when you add the triplet here because doublet. And again, the same logic. This guy is not singlet under S, and you can violate it either here or here. So it's very similar. The third variation is when you add the Higgs on the right side, then technically you need the doublets, and the S violation has to happen here or here. Okay, so in this case again, this is S non-singlet mandatory. The fourth variation is the so-called scalar seesaw, I think we called it. In this case, you add the second doublet, and you connect the neutrino left with neutrino right directly. And then if this is S not singlet, eta has to have the same transformation. Okay, same in this case. And then the mixing is what breaks the S. Okay, so the mixing can happen via another scalar or explicit, depending on the S nature, of course. So this is the 4 possibilities at the tree level. The loop case has only 2 possibilities if you attach the Higgs at the scalar line or the fermion line. In the first case, so if this is S not singlet, this is singlets, you can break S either here or here. And in the second case, you can only break here because this is the only soft term. Okay, so different UV completions possible here. We don't specify the numbers specifically. Okay, so in my case, to connect the neutrino mass model to gravitational waves, I extend the standard model by SUN dark symmetry, which is gauged. Box here represents the fundamental representation, and NF I put as a number of flavors of the kind. Okay, so there is 4 models here. I label them as 1, A, B, C, and 2. Okay, so in each case, the standard model extended by nu right, which is like the neutrino partner, and then technically it's the completions of the previous diagrams. The first model has the singlet, the second is a triplet, third is the doublet, and the fourth is the seesaw scalar, which is the second doublet. So here, one common particle to all is this phi, which is the dark Higgs, if you want to call it. So it's a fundamental representation under SUN, and that serves the purpose of breaking S and generating neutrino mass, obviously. Okay, so if we generate the neutrino mass, the diagrams look like what I showed before. This is model number 1, 2, 3, and 4. They all have the similar physics in the sense from the gravitational wave point of view. Neutrino mass is given by this equation, and this last one is given by this. And you can solve Yukawas using the Casas-Ibarra parameterization in terms of PMNS. So the potential of the model looks like this. So here I write the potential of the first 3 models, so not the fourth. So you have the Higgs, and there is a dark fundamental guy, which if you know call it dark Higgs. This is the Comet-Weinberg contribution, and this is the temperature. So we do this for the purpose of studying the phase transition dynamics, and in order to get the thermal parameters which would give us the gravitational wave signal. So in order to study the phase transition, we need to calculate 3 things: the nucleation temperature, the alpha, which is connected to the amount of energy released or latent heat here in the phase transition, and beta is like the speed of the rate transition or rate of the transition. Okay, so this is connected to potential parameters which are connected to the generation of neutrino masses. Okay, so the idea is that the gravitational wave signal depends on the potential, which also correlates with the neutrinos. Okay, and since we also have a dark matter, there is a possibility to connect it to dark matter. Okay, the phase transition looks like this. So this is the field, this is the potential, and for example, here is the potential at a temperature higher than the critical. Then when you reach critical, you have 2 degenerate points, and then the blue is at the nucleation, after the critical, when the transition starts, and this is the nucleation potential at the nucleation shape. At the end, the barrier disappears, so you have the first order phase transition, which can give you the bubbles, the collisions of which gives you the gravitational wave signal. So this case I particularly drew for these parameters in the potential, which is the strong first order. And our goal is to study the parameter space in such a way that you can correlate the parameter region where you have the correct neutrino mass as well as the detectable gravitational wave signal. Okay. So in order to connect these to gravitational waves, we use this kind of relations. So this was done from simulations by people in these references. So mostly I took it from David Weir's papers. He has very good reviews on that. So technically, the gravitational wave has 3 contributions in principle from the bubbles. It has the sound wave, the turbulence, and if I'm not wrong, the acoustic, I think the third one is called. So the dominant from the simulation, they showed that the sound wave is always the dominant signal. Okay, and the peak, the frequency peak is also determined by the sound wave. Okay, so we have these sensitivity curves from the proposed experiments. There is more like we have LIGO, then there is some other experiments here. But for us, the most interesting are this. So I'll list 6. This is the CMB constraint for plateau-like signals also. So our goal is technically to generate the signal which would be in this region. So we did some numerical analysis, and so for example, we generated some points like this for this one example of the parameter things, choice of parameters, which gives this black point, for example, which gives the correct neutrino mass as well as the detectable gravitational wave signal. So the idea is that, of course, not for all parameter region you can do this, but in general it shows that if we see the signal in the future, you could constrain, in principle, neutrino mass models using that data. Of course, under the assumption that the gravitational wave is somehow connected to neutrino mass mechanism. Okay. Next, after our breaking, when we break SUN by the fundamental, the remaining group is SUN minus 1. If n is not 2, then technically that group is not trivial. And after some running, you eventually get the confinement of that group. Okay. So this plot shows the correlation between technically the lambda d, which is the confinement scale of that remaining group, and the VF at the breaking of SUN, and the G at that volume. Okay, so this is curves for different number, the n being different, and the dashed solid is just the family difference. As you can see, when the n is large, it doesn't even matter. So the idea is that this means is that if the remaining group is not trivial, eventually you get the confinement, and from the confinement you can get the second gravitational wave signal, which is correlated with the first in our case. Because whatever parameters determine the first gravitational wave signal, they completely determine the scale and the degrees of freedom and everything of the confinement, which also affects the frequency and the omega of the second signal. Okay, so in this case we did analyze. So here you have to split. The important thing is that n equals odd and n equals even of the confining symmetry is different case. Because in our case we don't have mesons, the only possibility that can confine is either the baryons type particles when n is even because they're scalars, or if n is odd, then the only thing can confine is the dark glueballs. Okay, so here we use some lattice simulations to get this kind of plot. So this shows, this shows that so this is alpha beta of the phase transition. These dashed things are the experimental sensitivity curves. This is zoomed in at the beta between 10 to 3 and 10 to 6. And these different colors represent different temperatures of the confinement, technically, because the nucleation temperature is roughly the confinement. And the location on the curve represents the n. Okay? So technically what this means is that as n increases at a certain point, the alpha saturates, and it never depends on that anymore. Okay, but for example, this shows us that for this color, you can't probe it because the thing is above to the right. This orange is here. So starting with 10 to minus 1, for example, if the nucleation of the confinement point happens there, so 10 to minus 1, 1, or 10 to 1 GeV, then you get inside. So it's this green thing, the purple, green, purple, and red. Yeah, these three. So you can mostly probe this signal. So if they fall in, that means that in our case, if n was not 2 in the beginning, we could also see the second signal from here. And the two signals of the first and second transition are not independent. Okay, so they're correlated in this case. Then this is some plots for the dependence of nucleation temperature of the glueball case on this confinement scale and the number of colors confining, and so this is alpha beta plots. As you can see, this temperature goes linearly in principle. The alpha saturates, as was shown before, and it depends on technical NC just in the middle, and the beta. The interesting thing here is that first beta decreases, then increases. This is the effect of two fighting things, that there is a tension and there is a pressure. Before a certain, when NC is smaller than a certain number, this is 7, I think, you have one effect winning, and after that point, the other effect wins because of the number of degrees of freedom. Okay, in short, the summary is that if you want to get, or if you want to generate a strong gravitational wave signal, it's proportional to this thing. So it's proportional to the wave of the transition, or of the G of the group, the number of degrees of freedom that get the mass at the transition. So in some sense, the larger the n, the better for us. Then it's inversely proportional to G star, which is the lattice degrees of freedom, and the n of the group because of this, obviously. Some models that this have been studied in is the Petit-Salam, left-right models. I know some dark sector models have been done with this. So GOT is another possibility which Murai might have touched on this part. And of course, there is a confinement with all this dark quark story happens. Also possibilities the CFT, but I don't remember seeing them. Okay, the last word is on neutrinogenesis for us. Here, technically, this is the first three models. This is the fourth model. So you can make the interference between the tree level and the loop level like this. It would generate some non-zero CP from the Yukawas here. And in the second version, so the important thing is that in the first model, we need the VEV here. Otherwise, I couldn't do anything. In the second case, you don't need the VEV, okay? But it's a two loop. So I haven't finished the analysis yet, but I think the first case would be possible, but the second is more difficult. Okay, then one word about the parameters here. So in our model, even that it's pretty minimal in the sense that you want to get a drag with dark matter, drag neutrino masses. So we have the SUN n here, the number of flavors, which are correlated or constrained by gravitational wave signal and dark matter. The G, which is constrained by everything almost, though these things are fixed by standard model, standard picture. Then the VEV correlates with most of the things, including neutrinos and gravitational wave signals. This is the minimization part. Okay, anything that it's in potential effectively affects the gravitational waves, including the portal coupling. Then the Yukawas are fixed by mostly the PMNS part and neutrinos. And the heavy invariant scale is usually fixed by neutrinos and leptogens in this case, since it's involved in there. Okay, and so in the future, the possible things that we are planning to look at is study the correlation with the dark matter, of course. Then the GOT completions, I know some of them exist, but the advantage of this is that you can get the topological defects where you can generate more gravitational wave signals, which are correlated with the breaking, of course. And the other thing is the radiative neutrino mass models that we are planning to look at. So anyway, conclusion, done.
Questions or comments? So concerning gravitational wave strength and omega is squared, why is it proportional? Is it proportional to the number of color?
Which plot you talking about? Which plot or what you talking about? What is proportional to the gravitational wave square?
Omega is squared.
Omega, you mean?
Yeah.
The signal, okay. Let's go to the plot. You mean this, right?
Yeah, or maybe, yeah, next one. You got next one?
This one? No.
Next.
You mean this?
I don't remember. Yeah, this one. So
Mm-hmm.
I was wondering is the third and fourth.
So n is the n is the SUN. So technically it's the rank of the group -1 in that case. So the thing is this: when you do the phase transition, the more particles obtain mass from the transition, the stronger the gravitational wave signal will be. Usually that's the rule of thumb. Okay. So if you increase n here, that increases number of gauge bosons who get the mass, because that number is what that number was. It's n square minus 1 minus n minus 1 square minus 1. So I think that number is 2n minus 1, if I'm not wrong. Then you also increase the number of neutrino components, right? So and the confinement gives a strong gravitational wave signal if you have larger n, because of the larger the n, the more components confined in the baryon case, if I'm not wrong, that's why. But usually a real easy thing to remember is that the more particles get the mass, the better. But the downside is of course G star in that case.
Okay. So could you explain more about this rule of thumb? I just don't understand why is the number of the particles that get mass.
Okay, if I'm not wrong, the gravitational wave signal is proportional to alpha, right? It's an alpha dictated thing. alpha depends on splitting, right? At the nucleation part, correct? The splitting between the false and true vacuum. So there, the more splitting you have, the better, right? So if I'm not wrong, the n should affect that part. And the barrier is affected by the number of particles present, usually gauge bosons in this case. If you don't have gauge bosons, then it's difficult to generate the barrier. And the barrier directly affects beta. Michael Spanovsky has a good paper on that part.
Yeah, I don't know this subject well, but would you show the the energy density diagram
Of the gravitational waves? So the canonical things is that what people show usually. So there is a experiments, sensitivity curves proposed, and
okay, yeah.
This is the signals, yeah.
Okay, so the current advanced LIGO cannot detect the same, but future one, Einstein telescope or cosmic explorer. And how this suppose we have some data. What kind of physics in your neutrino model or neutrino masses can be
studied, constrained, tested, right? That's what you mean.
Identified.
Yeah.
Like that.
So let's say we see something like this in the future in one of the experiments. The only thing that you can know for sure that probably there is some phase transition, and you can figure out its scale and the amount of energy, right? So the rest we have to go from phase transition. So because there is a point on the plot, it can constrain two parameters. Okay? So usually these parameters are the portal coupling and the quartic coupling if you have one field undergoing phase transition. Okay, because there is usually a portal with the Higgs. So technically what you constrain is the parameters in the potential. Now the way I connect this to neutrinos here is that I'm introducing SUN, which serves three purposes. It generates neutrino mass, it gives the dark matter, and its phase transition gives gravitational waves. Okay? If my model didn't have a neutrino mass generated by phase transition, then it's nothing to do with it in general, right?
So then what kind of physical parameters we can
potential parameters. You constrain so the scale would constrain the wave usually. And the second, the amount would constrain some kind of number of particles. So it means that it's somehow connected to number of flavors of fermions involved, or if there's not that, then it would be the mass of the scale, I think. So usually you constrain the potential parameters of the phase transition.
Not the neutrino mass.
Yes. I mean, in my case, the potential parameters affect the neutrino mass. That's how I get this connection.
Okay. But according to your diagram, the advanced the future detector in the advanced LIGO bandwidth cannot detect the signal, but you need some more sensitive one in other band.
In this case, it depends on the scale, okay? Because if you want the LIGO sensitive thing, you want to be way to the right? Because LIGO is there, okay?
No.
Am I wrong?
Same bandwidth.
Okay.
As the Einstein telescope.
Wait a second. Yeah, you're right. I forgot that. So so usually here we focused on the transitions at the scale of 10 to 4, 10 to 6 GeV. If let's say I was doing phase transition at 10 to 10 or 10 to 12, like seesaw, then this wouldn't be there. Okay? Because if you increase the temperature or the scale where the transition happens, you increase the frequency linearly. Okay? So for GOT-like things, for example, what Moriyama have done, in that case, the normal transition happens way to the right. But in his case, because the object was the cosmic strings, the signature of cosmic strings is like plateau. So it extends all the way to here. But if you're doing the bubble collision case, then the signal looks like a peak. So if the transition temperature was way higher, then it wouldn't fall into this sensitivity range. So you cannot probe all the transition scales.
Okay.
So obviously you can focus on a certain limited parameter space. Yeah.
All right.
So,
question in your answer. Your gravitational wave generated from the bubble collision?
Yes, phase transition from the bubble collisions, yes.
So, means that the population, the regime, or
So here we use the equations for sound waves, right? So it's after the bubbles collide, yeah, I think.
Okay, so let's thank the speaker again. Thank you.
Hi.
So the next speaker is Inyong, and he will be talking about second
Okay. Okay, thank you. Today I'll talk about what is this? Okay. In Friedmann-Robertson-Walker universe, which means it is filled with perfect fluid, so in matter-dominated or radiation-dominated universe, I will consider gravitational scalar perturbations, and I will get the second order effective energy momentum tensor. Okay. Outline is first, half of this part, this talk will be given to the introduction to the cosmological perturbations. And I will introduce the second order perturbations and back reactions. There, I will get the second order effective energy momentum tensor, which I'll call 2EEMT in abbreviation. And I will discuss the gauge problems of this 2EEMT, and then I'll show several results in 3 gauge choices. Okay. As you know, in the Friedmann metric, with the Friedmann metric, perturbation can be written like this. Okay, this is the background, and this is the perturbation. Perturbation can compose of in all orders, so first, second, and whatever. Then I will write it in this conformal form. So this is the conformal factor scale factor. Then, as we know, probably know, that perturbation can be decomposed into 3, scalar, vector, and tensor, which means, like it's better to see this. Okay, scalar, here, phi, b, psi, and e, there are 4 scalars. And vector, there are 2 vectors, si, fi. And tensor, hij. This hij is like gravitational waves. In total, if you sum them up, then we have this in total. Then let us discuss about the number of independent functions of this perturbation. In 4-dimensional space-time, the Einstein tensor has 10 functions in general. This must have the same number. So we have 4 scalars, as I mentioned, phi, b, psi, e. And we have 2 vectors. So these 3 vectors, so 6 components. But there is a condition for this, divergence free. So we have 1 condition and for each. So we have only 4 functions left. And for hij, we have 6 functions, but we apply TT gauge, trace list 1 condition and transfer 3 conditions. So we have remaining 2 functions. So in total, we have 10 functions, independent components. Okay. Scalar part, actually it is most important because it is related with structure formation, density perturbation. Vector part is related only rotational motion of fluid, which decays very quickly. Okay, so it is not very interesting. Tensor part behaves like gravity waves, as we know already. Okay, so I will focus mainly scalar part. Now let us talk about the gauge transformation, coordinate transformation a little as a study. So from original x coordinate, we transform it by a small infinitesimal amount coordinate transformation, psi alpha. Then we will call it x tilde. Okay. This psi alpha, of course, is 4 vectors. So time part and spatial part, three components here. We can decompose into 2, like this one and zeta, some scalar function, derivative of scalar function. The reason why we decompose like this is this appears only in the vector part. So in scalar and in tensor, we do not have this. So it is better to use this. Then in scalar perturbation, we have only 2, psi 0 and zeta, freedom, degree of freedom. Okay. Then next one is complicated, so I'll skip this. Then what we are going to do is this. In the original x coordinate, as we have seen already, the scalar perturbation is like phi b psi e. Now we perform coordinate transformation. Then it'll change. In the end, we noted and denoted like phi tilde, b tilde, psi tilde, e tilde. Then these guys, red guys, must be different from the blue guys. The difference, so this is the red guy and this is the blue guy, and the other terms comes from the transformation. Okay, yeah. So derivation is in the front page. Okay. Then if you perform this to the scalar, we have this result. Okay. Psi tilde, psi, so the red guy, blue guy, and this is from the coordinate transformation. Non-trivial term appears here, and here, and here, and here. Okay? And we have, since chi 0 and zeta are involved, we have freedom to set them. Okay? So it means we can eliminate 2 of these variables, rearrange this, and then eliminate 2 of these variables and get only 2. Okay, by imposing these 2 conditions. So that's practically, you can say, gauge fixing. Okay. Yeah. So in doing, and as you know, because of this term, in different gauges, they look different. They are different. But if you combine them in some way, we can construct 2 gauge invariant variables, which is called Bardeen variables, investigated in 1980 by Bardeen. And this is capital phi is a composition of this actually. Okay, this and this. So this value is the same even after the coordinate transformation. So it is coordinate independent. So we call it gauge independent, gauge invariant. So we have 2 gauge invariant variables, which are called Bardeen variables. We can do the same thing for the vector, and okay, but just we can do the similar thing for the vector Sn as this one. Yeah, we have only 1 gauge invariant vector. Tensor itself, we have already imposed the TT gauge. After doing that, tensor is gauge invariant itself. Okay, so in all coordinates, Hij's are same. Okay. So gauge fixing means we can just choose this value of these 2 guys. Then this gives 2 conditions. Okay, then this is called gauge condition or gauge fixing. Then it means we fix the coordinate system. Okay. Example, the longitudinal gauge is actually B and in scalar perturbation, we set B and E are equal to 0. Okay, which is equivalent to psi 0 and zeta are equal to 0. Okay. Then the Bardeen variable is simply the origin of pi. Okay, this psi is small psi. Yeah, this psi. Then finally you can write the metric like this: 1 plus 2 phi and 1 minus 2 phi. So this is like Newtonian potential. So we call it, in other words, conformal Newtonian gauge. Okay. Okay. Now let's consider about the gauge invariance of Einstein's equation itself. Right? Then G mu nu equal T mu nu, this Einstein equation. If you extracted the first order, delta G mu nu and delta T mu nu, okay, each of them are not gauge invariant. So it means delta G mu nu, if you perform the coordinate transformation, the result is different from the previous one. Same thing, this one. But if you add, we can make this equation in a gauge invariant form. You can add the same term in the left and in the right. For example, 0, 0 part, you can add this amount. The B and E are gauge variables. Gauge variable means, yeah, it's gauge dependent variables. Gauge variable, you can add this term in the same way, T00, actually this is 8 pi G, T00 is G00, so they are the same term, okay? On the right hand side, you put this. Then, this guy, we can call it, this is delta G gauge invariant, or usually people just put bar here, okay? So this is gauge invariant tensor, and this is not tensor, gauge invariant quantity and gauge invariant quantity. So finally, we can write, for originally these guys are not gauge invariant, but this gauge invariant quantity, we can write it. So first order equation can be written in a gauge invariant form. So the result I can show you. We can write this delta G mu nu in a gauge invariant form means these components can be written by Bardeen variables, psi, phi, and psi. This D is phi minus psi, okay? Right hand side, we can construct as well as before gauge invariant form, okay? This is before gauge fixing. Okay, this is before gauge fixing. So first order equation can be written in a gauge invariant form before gauge fixing. Okay. So for the matter part in detail, for the fluid, we can construct this T mu, delta T bar as delta epsilon. Epsilon is here energy density. Sometimes I call it rho or epsilon. Epsilon minus this part gives the gauge invariant energy density part, okay? Like this. Yeah, you can construct gauge invariant energy momentum tensor. Okay. For the inflaton, which is a scalar perturbation, then if you redefine this delta phi by adding this term, then this is the gauge invariant quantity. So you can construct the energy momentum tensors in the same way. And also, for scalar field, we have scalar field equation. The scalar field equation can be written completely in gauge invariant way as well. Okay, this is the story of first order. Then, now my question is, what about the higher orders? Of course, this total G mu nu equal to T mu nu, this Einstein's equation is gauge invariant. Zeroth order, background is gauge invariant. We just showed this can be written in a gauge invariant form. Then what about second and third? As far as I know, we guess these guys can be written in gauge invariant form order by order, but from the second order, I haven't noticed any explicit form written in gauge invariant form. Okay, it must be very difficult, but have you? Oh, this work was done with this chairman, Jinuk Kong, and there, Seung Hun. Oh, Jinuk, have you ever seen such a? No, yeah. Okay. So now let us move to the second order perturbation. Okay, zeroth order is just the background, Friedman background. And then first order, I have already just mentioned about this. Then we can solve this as well, of course. Then solution, we get the solution. And we just plug this solution into the second order equation. Then we solve the second order equation, we get the second order metric. That is the story. And then you move further to the higher orders. Then let us look at this second order. This Einstein tensor part can be decomposed into two parts. in second order. First one is this. The metric itself is second order. Then linear terms of this second order metric is second order. Also, there are some quadratic terms of the first order metric perturbation. This guy needs to move to the right hand side. And then you can write this equation like this. So this was moved to the right hand side. Then with the original second order energy momentum tensor, this guy behaves as like a energy momentum tensor. So in total, sum of this gives the effective energy momentum tensor. Okay? And then this guy just affect this G2. Then if you solve this equation, you get G2. So this is called back reaction. Okay? So even for this meta part, we have linear part and second order linear second order part and quadratic second order part. So we keep this quadratic part for the inflaton, this delta phi squared term, and fluid delta rho energy density times G delta G. Okay, this is the quadratic term. We keep this. But the original second order one, delta phi second order, delta rho second order, we assume these guys behave stochastically. So the averaging of them give 0. Okay, we assume that. So this effective energy momentum tensor contains only quadratic terms. Then, yeah, this is how we get the back reaction. I mean, second order we solve. To solve the second order metric, just consider this effective energy momentum tensor and then solve the Einstein's equation. But in fact, to see the effect of this one, you don't need to solve this Einstein's equation. Instead, you can look at the form of this T mu nu. Then energy density and pressure, you can get the relation between them. Then you can guess what kind of fluid it is, what kind of matter it is going to be. That's what we are going to do. Okay. Okay. So now I will show what we have done. Okay. 배터리가 안 나와. Battery change. Okay. So original metric, you can say a function A, B, C like that. Okay. Yeah. Function A, B, C like that. It contains everything. So it is made of scalar, vector, and tensor. Sorry. Scalar, vector, and tensor in general. If you want to consider only scalar, then you kill this guy. This one, and this one. Then we are here. Actually, I changed the notation a little bit. This was phi before, but I'll say alpha. This was B, but I'll say beta. These are the same, psi and E. So metric is this. But I derive Einstein's equation in the original one, so A, B, C. Then Einstein's equation is already very complicated. I cannot put them in one page. So there is the IJ component. Energy momentum tensor part is a bit relatively simple. Here delta rho, here, and also A is the perturbation. So we will extract the quadratic terms here, okay? So what we do is, on the right hand side, T mu nu, we can just extract the second order quadratic terms easily. But here, we gotta take all the quadratic terms in the left hand side. That's very hard part. And then move those guys to the right hand side. Then that's what we call effective energy momentum tensor. Okay. Zeroth order, first order, I have explained already. The one thing that I mentioned is when the energy momentum tensor is diagonal, which means there is no off-diagonal term, this phi, Badin variable phi is equal to psi. So everything can be described by only psi. Okay? There are two gauge variables two gauge variables, which beta and E, but beta goes always E prime, so I will redefine it as Q. So in our notation, there will appear Q and E. Those are gauge variables. If those guys appear, it means that quantity is gauge dependent. Okay, if those guys do not appear, the quantity is gauge invariant. Okay. Okay. So I will evaluate this 2 EMT after some integration over several wavelengths. Okay. So I'll call it tau mu nu. Then I'll show the result. Okay. We perform the procedure that I mentioned before. Then T tau 0, 0 looks like this. This psi part is gauge invariant part. But inevitably, we get the terms containing Q and E, which are gauge variables. It means this quantity is coordinate dependent, which means gauge dependent. These are the same, okay? Yeah. So, what you can conclude, this is the first time actually to show that the second order energy, effective energy momentum tensor of fluid in an explicit form. So just we got the form, then we look at the form. If there are gauge variables, it is gauge dependent. Okay, so it is gauge dependent. The conclusion is this. Okay, second order effective energy momentum tensor of fluid is gauge dependent. Yeah, gauge problem. Long before, 20 years ago, for the inflaton field, it was discussed. Gauge problem was discussed. Second order 2E EMT was studied. First, Abramov, Brandenburger, and Mukhanov is over 22 years ago. Okay, they concluded, they did the same procedure as we did, and then they concluded 2E EMT is gauge invariant. 1 year after, Anu just wrote a paper. They are wrong, and there should be some gauge dependent. And much like 10 years later, Ishwash and Wild also argued more precisely it should be gauge dependent. Then why do they have different result? The thing is, these guys, when they do calculation, in the middle they fix the gauge, longitudinal gauge. So they got gauge invariance after fixing two conditions. If you do not fix those two conditions, that should be gauge dependent. They haven't shown it in an explicit form, but they proved that there should appear gauge variables. Okay? The result is the same for fluid of ours. Okay? Yeah. Then I'll show you several results with gauges. Okay, it is gauge dependent. Some physical quantities should be gauge invariant. In particular, if you want to detect it or if you want to observe it, it should be gauge independent. But I showed it is gauge dependent. Then, but in some limit, it can go to the gauge invariance may disappear. So that's what we are going to try. Okay. So we first choose longitudinal gauge, which sets beta 0, eta 0, then automatically beta plus eta prime, beta minus eta prime q equal to 0. So E and Q disappear in our result. So it can be written only psi. So it is gauge invariant, of course, after fixing the gauge. Somebody asks, okay, you fix the gauge, then it should be gauge independent. Yes, true, but not always. Some other gauge choices, like synchronous gauges, you fix two conditions in some fuzzy way, then still they remain in gauge terms, okay, gauge dependent terms. But longitudinal gauge, no, it can be completely gauge independent. Co-moving gauge, especially flat gauge. Flat gauge means psi 0, then finally Q is written by psi, Baudin variable. So this is gauge invariant after fixing gauge, okay? Co-moving gauge, VI, that the velocity, free velocity is this, and E equal to 0, then Q can be written by psi only. So again, you can write it. The result is only by psi. Okay? But as you have seen, forms are different. Actually, this guy is long. These F's are like this. Okay? Yeah. Then you solve the field equation and then put them in there and then look at some limit of that. If these three gauge choices, if the quantity just converges to one single value, then it means in that limit there's no probable gauge dependence. No, there is gauge dependence. Gauge dependence is very weak. Okay, we checked it. So in order to do that, as I mentioned, first order equation should be solved. So this is the first order equation. Okay, psi. We just impose Fourier mode expansion. Then solution, we get solution like this. For radiation dominated ether and for matter dominated ether like this. Okay? We plug this guy psi into the energy momentum tensor that we obtained before. Then I'll show only the dominant terms result. So in the matter dominated epoch, there are 3 gauges. The good thing is energy density. The result says energy density and pressure, both of them are proportional to 1 over scale factor squared, which behaves like curvature density. So K over A squared term in the Einstein tensor. But the bad thing is the equation of state parameter W, they are all different, which is different from curvature. Okay? Yeah, curvature density. So it means they don't converge. Next, radiation. First, in long wavelength limit, the result is very strange. 1 over 10, 1 over scale factor to the 10th. Okay, here, these two guys are different from this already. Okay, so this is not good either. And third, longitudinal gauge, short wavelength limit. Short wavelength limit, in this longitudinal and especially flat gauge, the result is very nice. Energy density decays like a radiation. And then even the equation of state parameter is the same with the radiation. So initially we just studied only these two. Oh, that's good. Then in short wavelength limit, we get some gauge, maybe we have some gauge invariant one. Behaves like radiation. But we tried the third gauge, co-moving gauge, but it gives us completely different answer. So this result shows that the second order and effective energy momentum tensor for fluid is completely gauge dependent. Okay? Yeah, that's our result. Thank you. Yeah. Probably no.
Okay. Yeah. You showed some solution in different gauges in the right part.
Yeah.
And that's the solution for the second order
2E EMT. No. We solved the first order equation and then second 2E EMT is the quadratic of this first order solution.
Okay. Even the solutions in first order equation depend on this gauge choices, you are saying?
No. First order equations are gauge independent.
Right, so that's why I'm confused, because this is just the perturbation, tensor perturbation, and the pressure perturbation relations with the scale factor.
Yeah.
Second order perturbation.
Yeah, only second part. Yeah, second order part.
Okay, the rho is actually the
second order. No. Yeah, that's right.
Okay.
Yeah.
That behaves differently.
Yeah.
Okay. Not so the whole density is the zeroth order plus first order perturbation and this one. Plus this one.
Yeah, surely. But yeah.
Oleg. Well, I guess the gauge gives different observers in general.
That's right.
So probably the definition of densities accordingly it changes. So I think this kind of different relationships with scale factor may be okay.
That's true, because energy density, and show here, is not a global quantity.
Right.
Energy density itself is a local, it is deep gauge observer dependent quantity. So next one is, with this result, maybe we can construct some gauge in invariant physical quantity. Yeah, but I don't know what that is going to be. But anyway, yeah, energy density itself is not gauge invariant. Yeah.
Okay.
Yeah. No, no question. Okay, don't.
Maybe it's related to the previous question that at the first order, can combine, for example, energy density and some other variable to make it gauge invariant.
Yeah, in first order,
So
yeah.
I guess something similar could be possible at the second order.
That's what you have to try. But because of this quadratic term, in the second, when you consider the second order, not purely the second order, but the first order squared terms, they will appear. So some people say they constructed a second order Badin variable, but I'm not so sure if it is really true or not. Okay, yeah. But anyway, in principle, I think it's possible to construct a second order, yeah, Badin variable.
So if I just add
Yeah.
one more comments, probably if you can roughly remember from the expression of the second order gauge energy momentum tensor, that is tau mu, if it is the gauge dependent variable is only the q variable, that's beta plus e prime, then you know that combination only dependent on the time gauge transformation variable.
Temporal.
So if it is given in that way, then probably there may be some hint to construct a second order gauge invariant variable, but the result is that it is not only dependent on Q, but also explicitly dependent on E. That also depends on spatial coordinate transformation.
Yeah.
So it does not come to very easily how to construct second order gauge invariant variable. So that's one thing I want to notice.
So in your discussion, you said some assumption about stochastic.
Yeah, that's right.
So how much that is reasonable assumption or physical minimum of that?
If you want to go to further order, I mean higher order, I think you have to keep those terms. Okay, yeah. But if you regard it as a back reaction for the second order, then usually that's what people do. But I don't know how physical it is. Yeah, really, yeah.
Okay, so if you have further questions, please ask me sometime later, and let's take a break.
Thank you.
좀 전에 왔다 간 사람이 열이 좀 있어가지고
그래서 닦았어요?
내 지금 닦는 중이에요. 기분 다 인지하는 것 같아. 감사합니다.
감사합니다. 알겠어요.
Okay, so the third speaker is CHOI from Seung Hun University, and he will be talking about dark matter and neutrino.
Okay, thank you very much for the invitation. So I will talk about neutrino oscillation and dark matter. Actually, this is a work with Eung Jin and Jong Kim at the KIAS, and then the paper of 1909 in the archive there. So basically, we want to explain the neutrino oscillations with neutrino interaction with the dark matter, not from neutrino mass. So neutrino mass is basically, okay, I can explain from this side. Until 1960s or 70s, I mean, neutrino was considered to be massless. So that is shown in the standard model of particle physics. You know, the neutrinos are massless. There are three neutrinos: electron neutrino, muon neutrino, hard neutrino, but those are massless. So in the theory. But however, there were problems to explain the neutrino number of neutrinos observed from the sun and also from this atmosphere. Because actually the number is smaller than the predictions with the massless neutrino. So that's the reason people considered the massive neutrinos. So then people had to extend the standard model to include the neutrino masses. So that was also presented in the previous talks. So there's so many models of neutrino. Basically, it's like this. In the sun, so neutrinos are produced, some electron neutrinos. But actually, the observed number of neutrinos on the Earth is different. Its number is smaller than the observation. So this is called the neutrino deficit problem and solar neutrino deficit. So actually, with the neutrino mass, people explain this way. So because, I mean, if the neutrino mass eigenstates are different from the interaction flavor eigenstates, then initially this blue is electron neutrino, but with the propagation, this is the distance, the fraction of the electron neutrino decreases and increases, oscillate. Because some fraction, it changes to some muon neutrino. So muon neutrino flavor increases, electron neutrino decreases, and they oscillate because of eigenstate or mass eigenstate difference. So this is solar neutrino. It is same for also atmospheric neutrinos. In the atmosphere, from the cosmic rays, muon neutrinos also are produced, but when we observe on Earth, on the ground, the number is also different. So now from these two observations, also with the other reactor neutrinos, people found that to explain these neutrino numbers, some mass squared difference, because for the neutrino oscillation probability, the relevant quantity are the mixing between different flavors, zeta, and also the mass squared difference of the mass eigenstates and the length and the energy. So basically, from this oscillation data, we can fix the mixing angle and the mass squared difference. So now, from solar neutrino, the mass squared difference is around 10 to the minus 5 electron volt squared order, and the mixing angle is sin squared zeta 1, 2 is around some 0.3. And from atmospheric neutrino, that the mass squared difference is around 10 to the minus 3 electron volt squared, and the mixing angle is some 0.4. We have only these two observations, but there are three neutrino masses. So one mass, actually, the absolute mass cannot be determined because we have only two conditions. So there is some normal hierarchy, some hierarchies. Actually, I mean, when there is a mass square difference in string generation in general, then the Hamiltonian for the neutrino oscillation in the neutrino interaction flavor eigenstate can be written this way: some delta m squared diagonal, and the U is the mixing matrix of neutrinos. This is the usual PMNS matrix with some many mixing angle and also the phase. So this is constant with the energy, and divided by this energy of neutrino, so roughly. So this oscillation, the Hamiltonian for the neutrino oscillation, Hamiltonian is written this way, can be written this way, with the massive neutrinos. So anyway, this can explain all the neutrino oscillation data very well up to now, with the massive neutrino. And also there is one more thing to explain solar neutrino. Important fact is the MSW mechanism. It's called this Mikheev, Smirnov, and the Wolfenstein. So this is not just from neutrino mass, but also the neutrino interaction with the matter in the sun. basically electron, proton, or neutron. So this interaction is weakly interacting. It looks very weak, but it's also very important to properly explain neutrino this deficit problems, because the interaction is like this. W boson interact neutrino and electron. In the sun, there are many electrons, no positrons, but there are many electrons. So neutrino can scatter, can have scattering with the electron. Actually, for the elastic scattering, actually due to this scattering, the mixing angle changes. If I say theta is the mixing angle in the vacuum due to the mass, but due to this interaction, this mixing angle, theta in the matter, changes like this formula. So x here is this quantity, the Fermi constant because of weaker interaction, and the n is electron number density. So the electron number density actually different for the space, point by point in the sun, and the energy of a neutrino, and the delta m squared. So like this, and also the mass squared, the difference in the matter also changes like this formula, which means that in the vacuum, mixing angle is theta, but in the medium, if x is the same as cosine 2 theta, then this becomes a 0, and is a 1. So in the matter, mixing angle becomes a 1, which means the maximal mixing. So more electron neutrino can change to the other muon neutrino, some things. So the number of neutrino actually changes, more changes. So this was important to explain the neutrino deficit problem. So it's called MSW mechanism in the matter. So this is just a standard mechanism. So we can write this way: neutrino Hamiltonian for oscillation is a vacuum Hamiltonian from mass of the neutrino, and also in the matter some this kind of MSW effect. This is in the sun only from electron. However, up to now there is no measurement of the neutrino mass. There is a neutrino oscillation we observed, but no direct mass measurement. We couldn't. There are many experiments like a neutrino restore beta decay for Majorana neutrino, or this Catherine, this tritium decay using tritium decay, and also cosmological constraint gives the neutrino mass should be smaller than some electron volt, but no measurement yet. But now our question is like this. Now it's okay. So neutrino oscillation is observed one. It's observation, so we need to explain. Up to now, this massive neutrino is a one good model to explain neutrino oscillation. Okay, so question is the opposite. So even though there is a neutrino oscillations, but can we actually you can say that neutrinos are massive or not? I mean, this direction is correct, but the opposite direction maybe not always sufficient condition, because if there are another models, if they can explain neutrino oscillation, okay, A and B, so which models are correct one? So we cannot distinguish with only neutrino oscillations. So we need more information to distinguish which models are really right model, right? Then the question is, then is it possible to have this kind of neutrino oscillations with some methods other than massive neutrino? Is it possible or not? So that's the main question here. So with the massless neutrinos, can you explain neutrino oscillation? And one possibility is we considered is that interaction between dark matter and neutrino. So the structure is like this. In the standard model, and the plus neutrino mass, the neutrino oscillation Hamiltonian is given this way. This MSW Hamiltonian plus Hamiltonian in the vacuum due to the mass of neutrino. But if in the standard model plus dark matter with the massless neutrino, if we can write MSW Hamiltonian should be there, it comes from standard model, but some potential from the interaction, maybe this potential is exactly the same as this H0 nu. Right. Yeah. Then you can explain the neutrino oscillation just in the same way as in the massive neutrino case. That's what we want to check. So can we create some potential from dark matter and neutrino interactions? Okay. So to see that, I mean, we can think again, this standard MSW effect is a neutrino interaction to electron with a W boson. So actually we calculate this diagram, scattering, that's easy. The potential is actually like this. Formula coupling and the electron and the positron number density in general, if there are positrons. And also here some mass of the W boson and the energy of a neutrino, electron mass, and epsilon. Epsilon is the asymmetry between electron and the positron in the matter. In the sun, actually there is no positron, so Ne bar is 0. And W boson mass is much larger than neutrino energy. So we ignore this energy dependence, and the epsilon put 1. That gives this value, plus minus square root 2 GFNE. That's some standard 배터리가 없어요. Yeah, standard result. Yeah. We consider same calculations in the dark matter interaction with the neutrino. So just as a simple example, we consider the Yukawa interaction. So nu is this neutrino, left-hand neutrino, and F and the pi is an additional new particle. F is fermion, pi is a scalar, complex scalar, dark matter we consider. So pi is a dark matter and F is some fermion, very light fermion. So in this case, neutrino, when it propagates, it can interact with the dark matter. Dark matter are around us, right? Dark matter. Also, there are anti-dark matter too, if we consider the complex dark matter. So then neutrino can have some matter potential. It's just the same as the MSW effect. The potential has also the same form as before. So it's a lambda is the G is the Yukawa coupling, lambda is the Yukawa coupling squared, like this, and also flavor dependent. And the rho over m is number density of dark matter. Epsilon is the asymmetry between dark matter and the anti-dark matter around our solar system. And the energy dependence is like this. In the standard model case, MSW case, the energy dependence was much smaller, so it was ignored. But here, if we may find that in the opposite limit, MF is very small, so only energy dependent term dominates, then this form potential looks like this is energy squared. It's like 1 over energy. So that's exactly the same form as the neutrino. 안 가네. 안 넘어가네. 어떻게 해야 되지? 네. 아, 그거 닦인다. 그렇구나. Okay, thank you. Power turn off. So I mean, we want this kind of form. Potential to be the same as H0 nu. H0 is 1 over energy. Okay, and some flavor dependent many things, but anyway, energy dependence is 1 over energy. So here, anyway, this term, second energy dependent term dominates, then we can obtain 1 over energy. Okay, and the other flavor dependent part, this lambda is a flavor dependent matrix. So this case and the Yukawa coupling, in some way has the same form to give the flavor dependence to oscillation. Then we can exactly obtain the same potential to give the same Hamiltonian from the neutrino mass. Actually, the potential shape is like this. When the energy is large, in the large limit of the energy, it looks like 1 over energy, but energy is very small than just the constant. So it's like this. Energy dependence is a constant and decrease 1 over energy. Well, this is dependence on the also epsilon, but the high energy is less 1 over energy dependence. So actually our observation for the neutrino oscillation is always a neutrino energy is larger than some mega electron volt. For low energy neutrino, we cannot observe oscillation yet. So this transition energy is smaller than some MeV. Then in the observational energy range, we always see that the potential is like 1 over energy. Okay. So anyway, we can consider this epsilon zero explicitly. It's not the really necessary condition, but so in this case, neutrino oscillations can be explained with the massive neutrino because the potential can be exactly the same as the Hamiltonian from the massive neutrino. So it's like this. In this case, potential is 1 over energy, and the flavor dependent and the normalization magnitude comes from this Yukawa coupling lambdas and this number dense rho over m dark matter squared. So to explain the neutrino oscillation, this lambda has if lambda can have exactly this matrix form and the energy this dependence of dark matter and the energy density of dark matter, then it can be explained. Maybe this should have some different signatures than usual this massive neutrino because this depends on the dark matter and its density in the our local universe. But dark matter is not just at rest. Dark matter has some velocity. So in this model, this neutrino oscillation can have some dependence on dark matter velocity, like some angular modulation, or some daily modulation, or direction dependent of neutrino directions. But the effect is actually very small because dark matter is non-relativistic. So this velocity dependence is somewhat compared to the neutrino oscillation. The correction may be some 10 to the minus 3 or some smaller than that. But anyway, this may be interesting to consider. So we are working on this now. And another point is that if epsilon is not zero, which means that dark matter and the anti-dark matter about number density are different in our local universe, then this symmetry, dark matter, can change the oscillation of neutrino, and the anti-neutrino oscillation can have a different effects because the potential has different sign from this neutrino, from dark matter or anti-dark matter. So if we observe the oscillation of a neutrino and the anti-neutrino separately, very, very precisely, then maybe we can see some differences which come from this dark matter asymmetry. So that's some maybe a way to observe, to measure the dark matter asymmetry in our universe from the neutrino and anti-neutrino oscillations. This is the example plot. So delta m squared is the observed from neutrino oscillation. Delta m bar squared is observed from anti-neutrino oscillations. In the standard case, it's just the difference are zero. They are exactly the same in the CP symmetry case. But in this dark matter coupling, then if dark matter and anti-dark matter has a symmetry, then if epsilon is non-zero, then they have some differences at some energy of neutrino. So that's another some important prediction of these interactions. 6 minutes. However, there are many constraints actually. It looks good, but there are many strong constraints between dark matter and neutrino interaction from some dark matter, because dark matter and neutrino has their interaction, dark matter can annihilation, or dark matter and neutrino can scattering. So they may change, they may affect this CMB anisotropy or large scale structure, or even this Big Bang nuclear synthesis or an effective number in the universe, or some neutrino flux or present observation of a neutrino anisotropy or many things. So these constraints are actually is very strong. I can skip, but so usually the constraint something missing. Well, if I can write this way, so this is a neutrino energy. This is a scattering, neutrino dark matter scattering divided by the neutrino mass, because some number density enters there. So from large scale structure, because of neutrino and dark matter, they have very strong interactions, then dark matter cannot grow at the small scale perturbations. So they constrain. The scattering cross-section is constrained to be smaller than some 10 to the minus 33 square the centimeter over GeV at the energy of a neutrino around the electron volt, because the structure formation they affected at that energy scale of neutrino. So it's a neutrino energy at around the electron volt. The elastic scattering should be smaller than this. Well, supernova 1987, at that time, the neutrino, some 10 or 20 neutrino was observed at that time. So flux was calculated somewhat more precisely. So if there are strong interaction between dark matter and neutrino, then the neutrino cannot come to us. So number is reduced. So to avoid that, the scattering cross-section should be smaller than some 10 to the minus 22. At this time, the energy of neutrino was around 100 MeV. So for 100 MeV, the scattering cross-section should be smaller than this value. Or much higher energy of neutrino, some 100 TeV, then this is ice cube, recent multi-messenger observation of ice cube. At this time, the distance of the source of neutrino was observed with other method precisely. And then we could calculate the flux of a neutrino in some way. So the number of neutrino not to be small, then the scattering cross-section should be smaller than some 10 to the minus 22 something. But the energy of a neutrino at this somewhere. Anyway, the scattering cross-section are constrained very well, but from observations, but all each of them are energy dependent constraint, right? So we have to use all of the constraints together to constrain some model. So in this case, Yukawa interaction, the scattering cross-section between dark matter and neutrino, something like this blue line, depending on the mass parameters. So for this solid line, in this case, this line alpha may be most important, but this dotted line, this ice cube is the strongest constraint, some that way. Anyway, it's a strong constraint. That's important. So this is preliminary, but if we consider this kind of constraints, then we find that some here, it's this purple line is the line to explain the neutrino oscillation. Then the dark matter mass should be smaller than some 10 to the minus 12 electron volt, very, very small. And the coupling, Yukawa coupling should be smaller than some 10 to the minus 11. So it's very, very small, not to affect the other observations, some things. Well, maybe okay, it can be small, why not, right? But so for that parameter, then the scattering cross-section like this, so they can avoid this constraint. However, there are also another possible problems, which means that, so now the dark matter is very light, but dark matter in this case cannot be fermion, should be scalar, but scalar is very light. But usually it's very light dark matter. Anyway, there could be more this cosmological constraint. So we didn't consider yet much of the early universe, some dynamics, or how this dark matter can be produced, or what's the normal density. But that should be considered more properly. Then maybe more difficult to make this model. Or also there's a classicalization. Some people says that with this very light dark matter, then the number of dark matter is very huge. In the Broglie wavelengths, in the value of the Broglie wavelengths, there are a lot of scalar particles. Then in this case, the wave functions can be somewhat classical. Well, I'm not sure about that, but in that case, if the this dark matter scalar becomes classical, then it can give a mass to the neutrino. Okay, then the neutrino becomes massive. And this can be some time dependent and also space dependent, then they can give the back reaction, not the back reaction, but again to give some neutrino oscillations. So then maybe something should be clarified in this matter, in this model. And also another question is that the number density, if the dark matter number is very, very huge, then the correction can be very huge and may maybe larger than the leading order calculation. So that also should be need to be answered in this model. So anyway, point is that neutrino oscillation is observed, but massive neutrino is good to explain that. But maybe we can think some other ways, not the neutrino mass, but some other ways may exist to explain neutrino oscillations. So we are trying to study with the dark matter neutrino interactions, but still there are many things to consider. The constraints that should be clarified. And another one is anyway dark matter asymmetry. If they have different dark matter and anti-dark matter different numbers in the local universe, then they may affect neutrino and anti-neutrino oscillation in different way. So that's some very good way to observe the dark matter asymmetry. Okay, thank you. That's all.
Questions or comments?
Very interesting idea. So basic idea is assume neutrinos do not have mass,
Yep.
but could have oscillations.
Yep.
Through some other interactions with dark matter.
Yes.
Okay. Then suppose the neutrino has mass
Yes.
and also interactions with dark matter.
Yep. That's also
And we
possible.
have both effects.
Yeah, sure. It's also possible. Yes.
But through the same form of matrix,
Yes.
can you distinguish?
Yes, that's yes, we can distinguish, but the effect is very small. At the present, with the present facilities, it cannot be observed, but maybe in the future, because maybe there is anyway differences. Because if it from interaction with the dark matter, then the part depends on the dark matter velocity. Then it can have some, as I said, some annual modulation or direction dependence. But the effect is very small. But still there is. Yeah, it's very small. But then maybe the way. And also the neutrino mass. Some neutrino mass, if the only oscillation is explained with the neutrino mass, then neutrino mass is determined up to overall value. But now the experiments which measure the neutrino mass, they cannot find some values until very low mass. Then, yeah.
Okay, in this model, the neutrino's mass is assumed to be zero,
Yep.
vanishing. So then, what will be the speed of neutrinos?
Light.
Always light, speed
Yeah,
of
yeah, yeah.
light,
Yes.
or effectively it gets some
It's the speed of light.
always.
Yes. If it is massless
Okay.
in the vacuum.
Then there is some way to measure such things.
Well, but up to now, even though neutrinos are massive, the mass is smaller than electron volt. But usually the neutrino energy is much larger than electron volt. So we cannot see the difference of the neutrino mass difference from the speed of light. Yeah, with this present observations. Yeah, yeah, okay, yes.
So even if there is a dense dark matter region and neutrinos just pass, speed does not change.
In the interaction with the dark matter neutrino, then speed may change due to interaction. Due to interaction. Yes, because the group velocity can change due to interaction. Yes, that's right.
So then astronomically, there is some way to see such a thing.
I don't know. Sorry, but the dark matter density in the astrophysical is much smaller than local dark matter density, 10 to 5 times smaller. So the effect is smaller. So maybe not that. I don't know. It's a much very dense. Dense dark matter region is not. In the center of a halo, galaxy halo, maybe more dark matter. Density is larger. Yeah, some things, but still flavor dependence are same of the neutrino oscillation, so it does not change it. But have to think more. Yeah.
Related with the Cosmology question, maybe from the supernova,
Yes.
you can compare the arrival time of neutrino and photon and some velocity of the neutrino could be. I mean, if the neutrino velocity is smaller than speed of light, then there is a possibility that neutrino arrive at Earth.
Yeah, but I think it can be small, but that's not that small. Okay, maybe have to calculate, but even though it changes, but I think it's not that big. No. I guess, maybe.
So for this effect to occur, you have to have some coupling between the neutrinos and the dark matter, right?
Yeah.
But this coupling with the dark matter field, it does not have to be something that is a dominant component of dark matter. It could be some field that is subdominant, any field. As long as you have some coupling to some field, then you claim that you can explain the neutrino oscillations.
Yeah, yeah. It does not necessarily to be dominant dark matter. Yeah, right.
Just some field.
Yes, but it should exist around us, around the Earth, around the Sun, because
right,
to explain
it doesn't have to have a measurable energy density at all. It can just exist some field that is larger than the vacuum.
Right,
and
but
because you have this coupling,
yeah,
you have neutrino oscillation.
Yeah, sure. It's subdominant and the coupling is larger, then they compensate each other. That's true. But as you said, there is upper bound for the number density of dark matter, or not the energy density of dark matter. If the energy density is subdominant, then it should be, the coupling should be larger, or some other, that goes somewhat more difficult situations you make. I mean, constraint should be, well, anyway, it's possible, yes. That's
have
just.
constraints if it's dominant component of dark matter. But otherwise, you could have any field.
Yeah.
Complete freedom.
Sure.
Just say that there is some coupling to some field that is neutrino.
Sure, if the matter exists around this Earth and the Sun, so that's fine. Sure, I believe. It does not need to be dominant dark matter.
Okay, so let's thank Inyong again. Thank you.
Thank you.
여기다 해도 되나요? 예. 그냥 그렇게 감사합니다. 시간은 저 오른쪽 위에 나오니까.
예.
Okay, the last speaker of the session is and we will be talking about cosmic conducting cubes.
Good afternoon. My name is Seung Hun, and I work as a postdoctoral fellow in Seoul Tech. And this work was collaborated with Dr. Canfora, Giacomini, Lagos, and Vera. And today I'm going to talk about the gravitating cosmic superconducting tubes in the Einstein-gauged nonlinear sigma model. And briefly speaking, our work is to find out the regular solution to the Einstein's equation, which is coupled to nonlinear sigma field and the Maxwell field as well. As is well known, the skyrmion was the first example of non-trivial stable topological soliton in three-dimensional spatial space, and it gave us fermionic excitations, even though the matter field is SU2 valued scalar field. And the skyrm theory describes the low energy QCD at the leading order in Lagrangian expansion of TOPT. And the SCUM model was obtained by adding the special term, which is called the SCUM term, to the nonlinear sigma model, which describes the low energy pion dynamics. And the reason why SCUM added this term to the nonlinear sigma model was to avoid the Derricks-Nogo theorem, which prevents the existence of the static topological soliton with finite energy. But in 1983, the Edward Witten showed that the fermion excitation can be explained based only on the existence of stable solitons with non-trivial third homotopy class, not based on the SCUM term itself. So we can naturally ask that is there another mechanism of fermion out of boson without SCUM term? We can expect the simple answer would be nonlinear sigma model couples to gravity, or nonlinear sigma model couples to gravity as well as Maxwell. And there were some attempts to solve these equations, and some of them were successful, and they found some exact solution of self-gravitating nonlinear sigma model with non-trivial topological charge. And the other way to avoid the direct Derricks-Nogo theorem was to introduce time-dependent S2-valued scalar field, but with the time-independent energy momentum tensor T mu. And another issue of the topological soliton is the regularity of the solution. And for instance, as you know, the Dirac's monopole in extended Maxwell theory has a singularity at origin. But Topte-Polyakov monopole in SU2-Yang-Mills-Higgs system is totally regular, and it has a finite energy. And at large distance, this monopole looks like a Dirac monopole. So we would say the non-abelian internal symmetry group can regularize the singularity. So, in our solution, we found a similar effect in the case of gravitating hadronic tubes as well. If the grand unified theory the idea of grand unified theory is right, then as the universe expanded and cooled down and went through several phase transitions, these topological defects must be formed. And because the most relevant interaction is the gravity in cosmology, so this topological defect should be studied in the context of the gravity. The simplest example is the cosmic string. The less considered the energy content, which is concentrated on the z-axis, which describes the cosmic string. The exact solution to this energy momentum tensor is very simple. The locally flat, but not globally flat metric given 2. Here, the polar angle theta, the period of theta is not 2 pi, but it has angular defect given here. And then, how can we regularize this singularity? There were some attempts, but some of them were successful in a sense, but in other sense, it was not. Because the one method was to smear T mu on a cylinder of finite radius, and some authors found the exact solutions. But still, this solution had the drawbacks because they contain a sharp boundary whose radius is arbitrary. And the T mu, their energy momentum, the energy momentum tensor they introduced was not derived from some fundamental action principles. So shall we abandon the idea of a cosmic string? No, not yet, because cosmic string can play a role in the galaxy formation as a source of density perturbation. And it can show a gravitational lensing effect as well as double images. And most importantly, it can show the superconducting effect proposed by Edward Witten, and the superconducting. If there exists this kind of superconducting strings, then it can be sources of synchrotron radiation or high energy cosmic rays or gamma ray burst. So, it is of great interest to find an analytic non-singular solution which can be derived from the fundamental action principle, which leaves no arbitrariness in the choice of field and their potentials and the parameters as well. So, In this talk, we will see how to construct the first example of analytic and singularity-free cosmic tube solutions for self-gravitating SU to nonlinear sigma model. This cosmic tube is very different from the nature of cosmic string. And at large distances, it looks like a cosmic string boosted in the axis and has an angular defect related to the parameter of the theory. But near the axis, it has no the conical angular defect. Thus, we found the everywhere regular solution, and the total angular defect depends on the distance from the axis in our solution. And the most important one is that our metal field do not have a sharp boundary, and the curvature reaches its maximum on a tube around the axis rather than on the axis itself. This is the reason why we call it cosmic tube, not cosmic string. Our solution, the situation happens in our solution is very similar to the monopole's history, because as 12th Polyakov monopole regularized the Dirac's monopole with non-abelian group, our nonlinear sigma model cosmic tube regularized the cosmic string with the SU2 group. And at large distances, the 12th Polyakov monopole looks like a Dirac monopole, but at large distances, our cosmic tube looks like a cosmic string. And this cosmic tube has a non-trivial topological charge as well, and it will show a persistent current, which is a kind of superconducting effect. And because this persistent current, superconducting current, are tied to the topological charge, so it cannot vanish. Let's start with this simple Lagrangian. Here R is the rich scalar, and L mu is the Moré-Cartan form of the SU2 group, and here kappa is the gravitational constant, and capital K is a coupling constant of nonlinear sigma field, and experimentally the K times kappa is 10 to the minus 40, fantastically small number. We follow the convention that the C and Haba are 1. The equations we have to solve are the nonlinear sigma field equation here and the Einstein's equation. The energy momentum tensor of the nonlinear sigma field is given here, and the winding number corresponding to this situation is given in 6. And this topological number is not 0 if the 7 holds. Which one? Pardon? Just the Moré-Cartan form here. Yes, because these equations are very complicated to solve, so we should choose appropriate ansatz for our space-time as well as the gauge space. For our for space-time, we take this Weil's canonical metric here. Here, the G depends on R and theta, and the capital R depends on R and theta too, and the B0, omega S, F0 are constants. And we choose the range of coordinate given here, R from minus infinity to plus infinity, and the period of theta is 2 pi. But this space-time is totally, absolutely Lorentzian, because the two-dimensional determinant of the TZ plane is negative definite.
Why there is theta dependence?
It's not correctly same as the Weil's canonical coordinate. We interchange the role of z, theta, and phi.
So G is not the coordinate along the string?
Yes. Z is the axis along which the cosmic tube located. Yeah.
And the theta is the angle.
Angle, right? Yes. But R is not radius. Please remark that this range of coordinates are.
I mean, why capital R?
Capital R is here. Yes.
Why that function of theta?
Which one?
G and R.
Yes.
Function of theta.
Because we are considering a non-axisymmetric solution. Yes. Yeah. Yes. So, and for group spaces, we parameterized the SU2 matrix U with the three Euler angles, alpha and cap theta and cap phi. Alpha depending on R, and the theta is Q times theta, and the capital Phi is a linear combination of T and Z. And we further assume that the phi is like, and the phi and theta hypersurfaces are orthogonal to each other. This conditions simplifies nonlinear sigma field equations very well. So the three nonlinear sigma field equations reduce to a single equation given in 13. This equation is very easily integrated to the 14 with the constant E0, but the compatibility with the Einstein's equation requires E0 should be 0. And the dependent Einstein's equations are just two equations given in 15 and 16. And here you can see that alpha and R can be, we can solve the equations for alpha and R very simply, but the G is a kind of two-dimensional Poisson equations. The solutions for alpha and R are found in 17 and 18. Here we have three integration constant, C1, C2, C3. C1 is nothing but a translation of the coordinate R, so we can forget it. But C2 is deeply related to the total mass of the cosmic tube, and deeply related to the regularity conditions. C3 is related to the regularity condition as well. So with these solutions, the equation for governing equation for G becomes 19. Let us impose the range of the parameter C2 given in 20. Then it makes our space-time totally regular and the energy finite, and the equation it makes the geodesic equations to very fine forms. And the energy density becomes 21, and we can find some geometrical invariant given in S, the rich scalar S here, and R square, and the Kretschmann invariant. But with this range of C2, all of them are regular, and the T energy density is finite. And the maximum value of energy density is achieved at the point where R is 0. But please remember that the range of R was from minus infinity to plus infinity. So the maximum value of the energy density is concentrated on the point finite distance apart from the source, from the axis. So we call it cosmic tube, not cosmic string.
Okay, so R equal minus infinity corresponds to the x-axis?
Yes. Okay, let me show you. Right. In order to analyze study our space-time, let us introduce a radial coordinate, capital X here. With this coordinate transformation, if we impose the same range of C2, then the range of X becomes from 0 to infinity. Okay, and our metric becomes this form here: dx square and the d theta square times g theta theta. In order to call this X radial coordinate, we should check the asymptotic behavior of the g theta theta here, right? So in the limit of R, as R goes to plus minus infinity, this exponential minus R goes to constant times X. So that the ratio of g theta theta at plus minus infinity is here and is less than 1. So we have an angular deficit. And please remember that in exponential minus R, we have another constant C3 here, and we can choose this C3 to remove the conical singularity along the axis. If we solve because we already know the exact solution of alpha and R here, we should solve the G. This is nothing but a two-dimensional Poisson equation. We can find the solution in a formal series expansions adapted to a boundary condition. Now let us generalize this solution to the gauged solution, which means the Maxwell coupling. Then we add a kinetic term of Maxwell field here, and our covariant derivatives would be promoted to include the A mu term here, and the field equations are given here. The current of the Maxwell field is given here, and its electromagnetic energy tensor is given in 29. And the winding number also includes the contribution from the Maxwell field as well. In order to solve the equations, we assume that the gauge potential has the form of this one. So it includes just one function u, which depends on r and theta. With this choice of the Maxwell field, the equation for alpha and capital R are the same as the non-gauged case, so we have the same solution here. And the Maxwell's equation reduces to a single equation, which is a type of two-dimensional Poisson equation 2. And the equation for G modifies to this equation to include the Maxwell contribution. And the energy density, the topological number density, and the currents are given here. Please remark that this current here, capital phi was an Euler angle of the SU to gauge space. A mu is the Maxwell field, right? Even though we turn off the Maxwell field, there would remain a persistent current because of non-trivial phi. So this makes a superconducting effect proposed by Edward Witten, right? With the choice of these parameters, we find 3 plots for alpha. Here, this is the graph of alpha, which is a typical graph for the topological solitons. And here, the graph of rich scalar, it shows regularity. And the exponent g theta theta here, in terms of capital X coordinate near the origin, and the asymptotic region, its behavior is like x squared. So we can call x radial coordinate. And the function g, this is the graph of function g, which shows that our solution is not x-symmetric at all. So this makes the analysis on the gravitational lensing effect very complicated because it's not x-symmetric. And here are the plots for energy density and the topological number density. It shows that our solution is totally irregular, doesn't diverge. And here are the electric field, magnetic field, and the currents here. In order to discuss the superconducting effect, let me summarize the Witten's argument. Witten introduced this, began with this Lagrangian. Here, he introduced the two kinds of Maxwell fields, A mu and S mu. And the A mu couples to Higgs field sigma, and the S mu couples to Higgs field psi. And so the symmetry group of the theory is U1 cross U1. And he broke down the U1, one of the U1 group corresponding to S mu, and it ensures the existence of vortices. And he assumed that the Higgs field psi depends on R and theta in the core of a vertex. And he chose the parameters so that the potential energy favors non-zero expectation value of sigma, but vanishing sigma asymptotically. So if sigma 0 minimizes the energy of the string, then superconducting current is associated with slowly varying phase big theta, and his ansatz is given in 34, and the current from this system is given in 35. The same structure, as you can see. If we turn off the A here, Maxwell field here, it shows the persistent current due to non-vanishing theta here. because theta was defined modulo 2 pi, so integral over a closed loop of the above current will not vanish. So even when one turns off the electromagnetic field. So this is a kind of superconducting effect. And such a current cannot relax when topological invariant associated to theta is non-zero. How can it happen? In 2013, Schiffman gave an answer. If we follow these three steps, we can get superconductivity. Firstly, let us begin with the bulk theory with unbroken global non-abelian symmetric group, such as SU2. And break SU2, this global non-abelian symmetric group, to a subgroup U1. Okay? And introduce stable potentials, then we will get superconducting effect. But our solution, Einstein-Maxwell nonlinear sigma field system, has all of these three ingredients already. So no, we don't need to, the very good thing of our solution was that we didn't need to introduce any potential. Very strange introduction. We could avoid a very strange introduction of two Maxwell fields, and we could get the superconducting current in 36, and it is a persistent current which cannot vanish because the topological number of our system is non-zero and it has a topological stability. Let me discuss finally. Let me discuss the gravitation, the peculiar feature of our solution for gravitational lensing effect. When we study the gravitational lensing effect, we just in many cases we just study the null geodesics, right? But roughly speaking, it means that we studied the sourceless Maxwell equation within the aconal approximation. So because it's a sourceless, it's massless. So its geodesic must be null. So we studied the null geodesic. But in our tube, our Maxwell field coupled gravity as well as nonlinear sigma field and the supercurrent. So if we regard the propagating photon as a perturbation of the background gravitating tube, let's call it A nu. Then the equation, Maxwell equation for this perturbation would be this one. Apparently, the right-hand side is not zero, so it has an effective mass term. So its geodesic would be time-like, not light-like. So these situations usually happen in Kinzberg-Landau description. So, in order to study the gravitational lensing effect or double image effect, we should consider the time-like geodesics for these equations. This makes our analysis on the gravitational lensing effect very complicated. Thank you very much.
Interesting solutions. Let me understand the situations first.
Yeah.
So let's take some limiting case.
Yeah.
It seems that there is a shift along the axis.
Yes.
So what kind of things make such there are some flow?
Yes, there is a supercurrent along the z-axis. So we cannot eliminate the dragging forces along the z-axis from our solution. We cannot eliminate it.
Even in the absence of Maxwell.
Yes.
Then you showed that the current is just a derivative of capital theta.
Phi.
I did phi.
Yeah.
And phi is g dependent. I mean
T and Z. Yeah.
T and G.
Yeah.
Okay, so flow goes along the z-axis.
Z-axis, right.
So that makes this dragging effect.
Yes. If we simulate the propagation of a charged particle, then as it approaches to the core, then at a certain point it will how to say, its trajectory would be the rapidly approach to the z-axis.
Okay.
Yeah.
Because of that dragging effect.
Yeah.
There is some critical surface, I guess.
Yes.
So you cannot stay at this constant g.
Yes.
In any case. Okay. Other one is this non-actual things.
Yeah.
So that's somewhat unusual. So is there any way to make it actually symmetric? Or this non-actuality is crucial to have this solution?
Yeah. I didn't include that part in this talk, but we cannot eliminate theta dependence. If we eliminate the theta dependence from the very beginning, then there is no solution such as this one.
Okay. So somehow this field prefers such non-actual configurations, or necessary to have such configurations.
Yes.
Then the question is the peak point of energy density.
Yes.
You showed the formula, but not graphically.
Yes.
For the energy density.
Yes.
So, but it seems that there is some tube-like energy density distribution away from the axis.
Yes.
But along the theta, the angle directions, there is some preferred.
In some part, the mass is concentrated. Yeah.
Concentrated on a circle.
On a circle.
With the theta dependence.
Yes.
Okay. Then the question is, if we just touch this and see the stability of your solution.
Yes.
Is it stable or?
Yes, it's stable. We made perturbations for our solution, and we showed that this solution is stable.
Stable.
Yes, at leading order.
Okay. Okay.
Thank you.
Okay. So because time is remote, so we should stop the workshop session here. So let's take the speaker again. Thank you.
Thank you.
And before we close the workshop session, there will be announcement by Professor Chen Wu.
Actually, there's not much to say.